Hello, Professor. I'm gonna zoom in a little bit more for we can see more better the video. So this is my reaction, and this is my completed mechanism right here. So we start off with chapter one. To start off with the basics for chapter one, oxygen, carbon, chlorine, and hydrogen are all examples of non-metal elements. The bond between C and O and H are polar. The bond is polar as oxygen is more electronegative than carbon and hydrogen. This makes an uneven distribution of the electrons bonded to them. This right here is an image of the oxygen being more electronegative, which means it's an S negative. Hydrogen and carbon are S positive, and this shows that these arrows are going different ways, different directions, making it a polar. If they're going the same direction, it would be a nonpolar. I will provide an image of a Lewis structure from a reaction. I will also provide a hybridized atomic orbital. This is my Lewis structure from a reactant, and they're all sp3s. It's upset these two C's because they have three orbital groups, making them an sp2 hybridized. And VSEPR theory for the carbon and hydroxide provided in my reaction is a 109.5 degree bent. It has two lone pairs and two bonds with four electron groups. Here's two lone pairs and here's two groups, making it four electron bonds. Yeah, four electron groups connected to them. Um, Finding the formal charge for my structure above, I will identify the formal structure for oxygen. Here's the formal charge, my equation, and this is my formal charge connecting all my numbers in that equation, which is a valence electron for oxygen is 6, subtract that by half. We put how many lone pairs there are. So we put 4 for having two lone pairs, meaning 4 electrons in total, and two bonds, making it 4 electrons in total, which we get a 0. This means it has no negative or positive charge. It's perfectly balanced with electrons. The last thing for chapter 1 is I will provide an orbital bond picture of my reaction and identify all the sigma and pi bonds. So this is my normal skeletal structure, and this is my orbital structure in total. So in total, we have 24 sigma bonds, and we have one pi bond for this. Chapter 2. To start off chapter 2, my leaving group is an OH hydroxide. It's a single covalent bond, and it carries a negative electric charge. HCl is a strong acid and OH is a strong base. The conjugate base for HCl is chlorine. HCl is a strong acid, which means that it donates a proton and a chlorine negative ion is produced. This makes chlorine negative a conjugate base. The conjugate acid for OH is a H2O water. The nucleophile in my reactant is in my reaction is a HCl, and the electrophile is the OH bonded to my reaction. In chapter 2, we learn about the Lewis acid electron pair receptor and the Lewis base electron donator. For the Lewis base, it must have at least one lone electron pair. The Lewis acid must have a low energy empty orbital or a polar bond to hydrogen. For example, in this reaction, it shows that my oxygen has two lone pairs, making it my Lewis base, and the Lewis acid is my acceptor for HCl. The HCl is a polar bond and it's making it my electron acceptor. In chapter 3, we learn about the functional groups. Some functional groups in our reaction would have an alkene and an alcohol for my reactant. This is my reactant for my reaction group. An alkene contains a C plus H only, and it also contains a double bond. An alcohol contains a hydroxyl group behind it, bonded to a carbon. Also, it's an sp3 hybridized. My product has a functional group called an alkyl halide, also named as haloalkane, and it contains a halogen bonded to an sp3 carbon, shown below here. My nucleophile for my mechanism is a chlorine negative, which is an electrical negative atom with lone electron pairs. My electrical file for my mechanism would be this image of a structure of my mechanism because it's electron poor with that carbon, needing more electrons with that cation as well. Dipole-dipole interactions are between polar molecules and the S plus atom of one molecule that has to be attracted with the S negative of a neighboring molecule. For example, this oxygen is a S negative neighboring with an hydrogen, chlorine. So since this hydrogen is S positive and this oxygen is a S negative and it's connecting to each other with an arrow, this becomes a dipole-dipole. It also has attraction to the long dispersion forces LDF because the molecule has electrons in them. Identifying what element has the strongest LDFs and needs to have more electron energies to break connections and solid that tend to be the strongest. Not just that, but a stronger LDF can also be the molecules with the bigger surface area. And I will compare and contrast the different IMFs from my reactant products. So for example, my reactant and my products, they are this one, my reactants an alcohol, my products an alkyl halide. They're both polar. They both have dipole-dipole because of the S negative and the S plus, and they are both LDF. The only thing is that my reactant is a stronger IMF for having an H bond connected to the oxygen. My product does not have that, so it's a weaker LDF. Not just that, but my reactant is also a higher boiling point than my product does. Chapter 4. Throughout Chapter 4, I learned about cis and trans isomers that exist in molecule structures. In my reaction, I have a trans isomer located in the alkene. If I was to draw a line right through that pi bond, my two groups are opposite sides, which makes my reaction structure a trans. It's not a cis because it would be on the same side. Here in this image, I drew a line on my alkene and I put the higher priorities, and so far this makes it a trans because they're both on different sides. If they were on same sides, like both right here, it would have become a cis. A Newman's projection for my structure, you have to circle the ones nearest the middle. My left side of my structure has two H's and it has a CH3. My right side of my structure has a chlorine, hydrogen, and a CH2CH3. So we transform that into a Newman's projection, showing that we have two hydrogens and a CH3 on my left side and my right side connected to this part right here in the middle. And this is my Newman projection for my product and my mechanism. Here, I'm gonna demonstrate what's staggered and what's taking eclipse for that exact same structure. So here I provide a staggered, it has a steric strain and it has no torsional strain. But my eclipse does have a torsional strain and some steric strain because they're so close to each other right here, making it more packed. So the more packed they are, they become the more steric strain they have. For chapter 5, I learned a technique using the RS configuration. The way to find an RS configuration has 4 priority rules. Number 1, higher atomic number. The higher the priority. Number 2, if it's bonded to the same type of atom, we look at another atom. Number 3, it's different isotopes. The higher the mass number, the higher the priority. And number 4, treat multiple bonds as being bonded to that H of atoms. So for example, using both of my products on my mechanism, I will provide how to solve for the RS configuration. They both have a chiral center, and we number the highest priority, which is chlorine because it has a stronger electronegative. Then we number this one. Next, number 2, because it's longer than this carbon. This is the third, and number 4 is hydrogen, which is way weaker than all of those 3. So when we circle around this, we go clockwise, which makes it an R. Now, for this one, the direction is R, but I know my answer is backwards because hydrogen is coming out instead of going back, making it making it an S. The lowest priority group is forward, so then we reverse the answer. So it is clockwise, but we switched up the answer to an S because of that hydrogen and that chlorine going different, going forward and backwards for the hydrogen and chlorine. Drawing all possible stereoisomers for my reaction structure. To find a chiral center, the compound with the carbon atom must have 4 not identical substitutions. In other words, it's non-superimpossible on its mirror image. Here, we do have 2 chiral centers, making it have 4 stereoisomers altogether. Learning about racemic mixture, my products from a mechanism is an enantiomer. It's not identical meso or diastamers because it's a chiral molecule that has a mirror image of one another. It's non-superimposable imposable on one another. It can be placed on top of one another and expect the same molecule. So this is an enantiomer. Chapter 6. The type of reaction I have is a substitution reaction. Here is a demonstration of a substitution reaction. Demonstrating my curved arrows showing all electron movements, I will provide all the curved arrows and electron movements. Here I provide all my arrows showing how all my electrons are moving around. And this image right here is a carbocation, not a carboanion, because it's unstable by being a non-octet. My reaction is a SN1 reaction. It's best in the third and second degree ROHs. The carbon in it is an sp3 hybridized with a second degree ROH. So for this image, the carbon is sp3 hybridized, and there's this carbon is connected with 2 other carbons, making this a second degree ROH. The nucleophilic substitution from a reaction when I talk about my leaving group. My leaving group is bad in this reaction. So the first thing we do is we make the leaving group better. By that, why do we make it better? The reason for this is because a better leaving group can best accept the electron pair. This structure is a bad leaving group, which is a halogen. To make it better, I have to make it into a water, which I do right here, making it a better leaving group than this. In my mechanism, I have a structure that is a carbocation and need to be fixed. To make it more stable, we move the hydrogen to the least stable carbon and switch the cation to the more stable side of the structure. This is called a C plus rearrangement. Also, it's using hydride shift to make the carbon cation more stable, moving the electrons bonded to an H with adjacent carbons. Here is an image of me moving my hydrogens, making it a second degree to a third degree. We want the most stable, not the least stable. And here's a demonstration of my energy diagram for my mechanism. So this will match my mechanism. Chapter 9. Naming my reactant and product structures in IUPAC nomenclature with correct stereochemistry. I will be using my reactant and I will be using my product. For my reactant, it is called E3-methyl hept 5N2O. We do have one substitution on the third. So we start off with the first substitution, which is 3-methyl. That substitution is a methyl. Hept, because there's 7 on the long chain on the chain. We do have 7 carbons, which makes a hept. Number 5 because of the alkene, but we're not done there. We always start off with alcohol, but we finish it in the naming. So 5N2O. So this will be my name for my reactant. And the reason why it's an E is because it's trans. So if we make a line here, this would be, if we make a line here, this carbon would be greater than this hydrogen connected over here. And then we have another hydrogen here, but this carbon is also connected, which makes it opposite. Like I said, it is a trans, but we also name it as E. It's not a Z or a cis. Same goes for my product. But for my product, the chlorine is on number 5. So we start off with the substitution 5-chlorohept -2, and then we end it with the ene since we don't have no alcohol. My reactant I created is an alcohol for the OH connected to the carbon. My reactant only has an ROH. Learning in chapter 9, we learned all kinds of epoxides, alcohols, but I chose alcohol for mine, and here's a demonstration. And that will be all for my presentation. Thank you so much. Thank you. Bye.